Okay, let's start our lesson today. Last time we looked at isomerism, where we're looking at how to map points of one elliptic curve to another elliptic curve, to points of another elliptic curve. At this time, we want to see how to do elliptic curve point compression. Compression is important just to ensure that storage, you minimize on storage and transmission size. So for instance, if you have points in the traditional form, the way the points normally are, to store them, it will take a lot of space. So we need to compress them so that then we can minimize the size, the storage size that we supposed to use. So that is what we mean by compression. So we'll be looking at how then we compress points of the elliptic curve. Look at several examples of how to do that. And then of course, look at how to write code to assist us in doing the same. So just as I've said, that if you have points of the elliptic curve, to compress those points, what we are saying that this is a technique that will be used to reduce the storage and the transmission size of these points. Now, if we have points in the compressed form, we are saying that an elliptic curve is then represented by a small amount of data. If you have you compressed those points, then we shall use a smaller amount of data compared to the uncompressed form. So that's what we want to then achieve. Now to compress, supposing I had 52 bits. So I'll then compress it to, no, if I had 512 bits, I'll then compress it to 256. So that means the storage that I'll be using then will be a half of what I will have used initially. That's what it then means. Now we'll then see also how this is applied in cryptography because it's a very important concept. So we'll see how important it is. Just before we go into compression, I want to recall something. If this is our elliptic curve, it's symmetric about the x-axis. This is our x-axis, it's symmetric. Now what we discovered is that if you have this point, and let's call it point A, xy, this is a point A, its inverse is on the other side of the x-axis. Its inverse is on the other side of the x-axis. Of course, these points will be on the same vertical line. So its inverse, which we just write as A inverse, this way, is this point, x negative y. That is the inverse of this point. And then if you have another point here, let's say B, and let's call it AB, its inverse again will be on the other side of the x-axis. Its inverse will be here. Let's call it B inverse. And the coordinate of this will be A negative B. That's the coordinate of that. Now, so what are we then, if we were to compress, we will use this knowledge that every point has its inverse. Every point has its inverse and is on the same side. So what you discover that at this point, A and its inverse have the same x coordinate, have the same x coordinate. The y coordinate is the same but different in sign. Same thing to this point B, have the same x coordinate, but the y coordinate is the same but different in sign. So that's what happens to every point. Every point, apart from those points that lie on the x-axis, like a point like this one, a point like this, which would then lie on the x-axis. This point will have only, it will only be one. this point, it's its own inverse. This is its own inverse. So see, if this is, let me say, -2, -2, 0, then this point is its own inverse. So it exists only, there is no other point. There's no other inverse of this point. It's its own inverse. But the rest of the other points will always have a point above and another one at below it on the same vertical line. Like this is above and there's another one below it. So every other point will behave like that, apart from those that will lie on the x-axis. Of course, there will not be many. But the rest will be appearing, having 2 points where the x-axis, the coordinate of the x-axis is the same, and the y-axis differs by sign at the same value. So that is what I mean by symmetry of the elliptic curves. And this is what we'll be using. So then to compress this point, what we then discover, again, just to remind you, supposing we are dealing with our P, which is 7, supposing our P is 7. Now let me come back to this point A. If this point A is 2, 3, if this point A is 2, 3, then I expect its inverse to be 2, -3. But -3 is 4 mod 7. -3 is 4 mod 7. So that's what I expect. So what you discover is that these 2 points A and B, now A and its inverse, the sum of the y coordinate is 7. It sums to P. The sum of the y coordinate is 7, sums to P. So supposing our point B here is 1, 3. Oh no, let me say 1, 2. 1, 2. If this is our point B, then the inverse of this point would be 1, 5. So that the sum of these 2 points is P. Is that okay? So the sum to P, or P7. Of course, if you had to use this, we expected that it's 1, -2, but -2 mod 7 is 5. So just add 7 to -2. So this is what we'll be using to compress our point. So you realize that in this point B, the y coordinate is what we'll be changing. The x coordinate, we store it. We store the x coordinate. In our compression, the x coordinate is stored, but the y coordinate is the one we want to make smaller. This is the one we want to make smaller, but the x coordinate will remain. So that's what I've said, that we can represent each point on the elliptic curve. To compress, what I mean is we represent each point on the curve using the x coordinate and a single additional bit. A single additional bit in place of the y coordinate. In place of the y coordinate, we are using this single additional bit. But where the x coordinate is, it remains. So that is what we will then be doing to compress. Of course, I'll come to that technique. I'll come to the technique here, how to compress. Now, this point I've already explained, that if you are dealing with, let me say, 5, 12 bits, then to compress, you want to get a half of this. And so you'll be talking of a half of that. Now, so I've already explained about point and its inverse. Of course, this is just a reminder of what we had already done. the inverse of points on the elliptic curve. Like the inverse of xy would be x negative y. And since we are dealing with the mode P, the negative y, you just get it by adding P to it, then you get a positive value. Now, so how do we compress? I've already mentioned that. I've already mentioned what we'll be doing. That we'll be storing the x coordinates, and then the y coordinate will be representing it by a single additional bit. And so that as single additional bit is the part that I now want to just discuss. Now, just again, a reminder, I've said in the elliptic curve compression, each y coordinate for a given x coordinate has two possible values. What I mean is if I have point x, no, a point A, the coordinate for this will be this, and its inverse, the coordinate will be x negative 1. So that means every x coordinate has two y values. Every x coordinate has two y values. And of course, I said this will be only different for points that will lie on the x-axis. Those are the only points that will have the x coordinate having only one y coordinate, y value, which will be 0 in this case. But every other x value would have two y values. So I expect, therefore, for instance, that at this point, as x value as that, if I'm dealing with the mode 7, I'm just taking this as an example. I'm not saying that this is a point on that elliptic curve. I'm expecting this also to be there. And so if I have 2, 3, I'm expecting 2, 4. So that the y values always add up to p. Every x value has two y values. That is what this point talks about. Now, these values are symmetric around the curve. This one I've already explained. Now, let me come to then what we are adding, how we are working with the y value. I said while compressing, the x value remains, but the y value, I talked of some additional bit. Sometimes we call it the sign bit. Now, this is what will be used to differentiate between these two values, these two y values. The x value is the same for the 2 points, but the y value is different. And this y value is the one we want to change. So then we come up with something I call the sign bit to differentiate between this large value and this smaller value. This large value and this smaller value. Now, so the large value, the smaller value, first of all, we replace it by a 0. And then the large value will then be representing it by a 1. The large value will be represented by 1. So if I was to compress this point, therefore, to compress this point, the point that I get will be 1, 0. That is my compressed point. This is the uncompressed point. Its compressed form is 1, 0. And this one, its compressed point is 1, 1. Let me now compress these two. I compress these two. This will be 2, 0, and this will be 2, 1. So these are the compressed forms. So the larger value of y, you give it 1, and we are calling it a sign bit. Its sign bit is 1. And this other one, the smaller value of y, its sign bit is 0. So that's what we then be doing to compress. So it's a very easy technique, therefore. It's a very easy technique to compress points on the elliptic curve. So let's just take a few examples because it's a very easy thing. Then we move something else. So just to make the example, as an example, I want to consider this curve mod 13. This curve mod 13. Now, this curve has this point 1, 2. 1, 2. So I expect to have another point 1, 11. I expect to have that other point. Is that okay? Yes, because this point is not on the x-axis. So I expect to have its inverse. And its inverse will be 111. So that 11 plus 2 will give us 13. Now, so if I was to compress this, now to compress this, it will be 1, 0. And the other point, which is 111, will then be compressed as 1, 1. Because 11 is the bigger value than 2. So the bigger value then takes the sign 1, the sign value 1, and the other one takes a 0. So that is then how to compress. So you realize that you then be dealing with a smaller size. So they not take a lot of space to store these new values. Now let's assume that we're now working mode 7, and this is the curve that we want to work with. So in fact, what I was doing here, I then found the points of this curve. This one we know, we already know how to get the points on this curve. How to get the points on this curve. You can use a code. You can use a code. If you don't want to use a code, you can always do that. Let's just, but you can use a code. And suppose you don't have a code, let me again explain how to get these points. We are doing it mode 7. So we will take the x values to be 0, 1, 2, 3, 4, 5, then 6. Those will be the x values. So we want to get the y values. Want to get the y values. But before you get the y value, you have the y square, then come up with the y value. So how do you get y square? You just substitute your x here. That is, let me substitute x, which is 0. So that would be 0 cubed plus 3, 0 plus 4. So that means y squared, therefore, when x is 0, y squared is 4. So what is y? Y will then be the square root of 4, and that will be 2 and 5. That will be 2 or 5. The square root of 4 mod 7. Because it will be 2 and negative 2. Is that okay? Then negative 2 mod 7. That gives us 5. So when x is 0, we have these two y values. That's what you see. That's why you see that then we shall have a point 0, 2. 0, 2, one of the points, and then 0, 5 would be another point. 0, 5 would be another point. What about when x is 1? Just substitute 1 here. To be 1 cubed, which is 1, plus 3, 1, that gives us 4. Then plus 4, that would be 8. So y squared is 8. And so what is the square root of 8? Of course, 8 is mod 7. 8 mod 7, this is 1. 8 mod 7, this is 1. Is that okay? Don't write a value that is more than 7 here. Now, so the square root of 1, therefore, is what we call y. The square root of 1 would be 1 and 6 mod 7. Because the square root of 1 will be 1 and negative 1. Is that okay? So 1 is 1 and negative 1 is 6 mod 7. And so on. So this gives us a point 1, 1, another point, 1, 6. So every value that is not the x-axis is giving us two coordinates. Every x value that is not on the does not lie on the x-axis. Okay, that has a y value that is not on the x-axis. Then that we shall have two y values for that case. So you can see when x was 0, we had two y values. When x is 1, we have two y values. When x is 2, we would have two y values. When x is 3, it's not possible. X is 3, there's no coordinate. That is why you see, when you substitute 3 here, substitute 3 there, the value that you get would have no square root. Would have no square root. That means there's no y value for that. Now, so this, if you do that, you then get all the points of the elliptic curve. We've already obtained 4. And the other point is the point at infinity. It's another point. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. That is not our point today. Our point was, first of all, how do we now compress these points? Is that okay? So we get them, then you compress them. Now to compress them, we've already said, like the point at infinity is already in its compressed form. So it just remains that way. Even in the compressed form, it remains that way. Let's compress this point. This in its compressed form will be 0, 1, no, 0, 0. It will be 0, 0. Is that okay? And this in its compressed form will be 0, 1. This will be 1, 0. And this will be 1, 1. This will be 2, 0. And this will be 2, 1. This will be 5. You can see that, okay, that is 5, 0. 5, 0. Then this will be 5, 1. Now, this one is the point we are talking about. The y coordinate is on the x-axis. Is that okay? Lies on this horizontal line. So it's already in its compressed form, the way it is. It remains that way. Now, so that is how we store points of the elliptic curve. That's how they are stored, to minimize on storage. But then later on, you may want to get your points back. So you already know if you have to get it back, this is what you do. First, I want to get it back. I know that these points are already compressed. So I know that the 0 one here, the one that has 0, was the least of the y's. This one was the highest. Is that okay? So, but what I want to, that is not even important. What I want to get is, I have this point 0, 0. And I have this point 0, 1. I have this point 1, 0. I have this point 1, 1. And I want to get my original points back. So if I want to get my original points back, I just come to the equation and substitute the x value back. Substitute the x value. So for instance, in this case, when I substitute the x value back here, I'll get 0 plus 0 plus 4. So y squared will be 4. Then I get the square root of this. The square root of this will be 2 and negative 2. Negative 2 is 5. Is that okay? So these are the two y values I've obtained. When I come to this sign, the sign here, which is 0, I know that it stands for the smaller of the two y values. Is that okay? This 0 stands for the smaller value of y. So I know then the original y for this sign was 2. So I've obtained my original point back. And then I have this 0, 1, 0, 1. So I know that then this is what 5 was the original point. So what I mean is, if you find points in compressed form, you can always obtain the original points back. Is that okay? Yes, you can always obtain the original points back. So this again will be very important, of course, when you go to elliptic curve cryptography, because then they'll be using compressed points. They'll be using compressed points. Even in doing encryption and decryption, be using these compressed points just for reasons of storage and transmission. And so it's always easy to obtain the original points back from the compressed ones. So at this point, what I was doing, I was trying to compress. I was just compressing. I was saying that this will go to 0, and I was giving a reason that is since y is equals to is smaller because the other one is 5. 5 is bigger than 2. So the 5 one now becomes 1 because 5 is larger. Then when you come to these 2 points, this one goes to 0 and this one goes to 1. When you come to these other 2 points, this one goes to 0 and this one goes to 1. And so on. This one goes to 0, this one goes to 1. And this one, it remains as it is. So that means we now have the compressed points. We have the compressed points, and I've written them here now as the elliptic curve. And you know, when you get this, you must understand what it means. This elliptic curve is just saying that the f value is 3 and the y value is 4. And so, of course, in this curve, we are doing it mode 7. So when you find this, you then understand this is the elliptic curve, x cubed plus 3x plus 4. So that's what it means. But this is now the compressed one. And we had done compressed one above. I've already talked about how to decompress, but we can just repeat. I've already talked of that. How do you decompress? If somebody had given you compressed elliptic curve, how do you decompress? So to retrieve the original point, we note that the x value did not change. The x value did not change. What only changed was the y value, and we had replaced it with a bit, the sign bit. That's what we had replaced it with. And so we also note that at several points, the x value would have 2 y values. And the smaller of the 2 y values will have 0 in its compressed form. And the larger of the 2 y values would have 1 in its compressed form. So then for us to decompress, just take the x value and substitute back in this equation, the original equation of the elliptic curve. And after that, look what the 2 y values that you get. And the smaller one, replace it where the 0 is. The larger one, replace it where 1 is. And you will have decompressed your points. You'll have decompressed your points. That's how you do it. So yeah, this is an example. Decompress this point. This point, the elliptic curve was y square is x cubed plus 3x plus 4, and we are doing it mode 7. So to decompress this point, just substitute 2 back. When you do that, you get y square is 2 cubed, and then 3 times 2, then plus 4. Of course, this is 8. We are doing that mode 7. This becomes 1. Is that okay? This one becomes 1. And this is 6 plus 1. 6 plus 1 gives you 0. Is that okay? mod 7. Is that okay? 6 plus 1 gives you 0. Then plus 4, 0 plus 4, you obtain 4 mod 7. So y squared therefore is 4. Y squared is 4. What about the square root? What about the square root of y? The square root of y will be 2 and negative 2. And of course, negative 2 is 5 mod 7. So the square root, which gives us our two y values, are this. Our two y values are this. Now, this point was compressed. This is a compressed point. So that means this one is the parity sign. It means the point that was here, the y value that was here was larger, the largest of the two. So it means 5 is the one that was compressed. So that means, therefore, the original point was this 2, 5. That was the original point. So it's very easy. This is a very easy concept. And of course, we will see how to write a code to do this, code to compress the points for us. Before that, we look at the advantages and disadvantages of compressing points. Of course, one of the advantages we talked of is the space. We reduce space required for storage and transmission. Yeah. The element and just one bit. Just X and one more bit. Yes, yes, yes. So one more bit. Okay, then about the challenges. The only challenge you have about this is finding the square root. Computing the square root sometimes is not very easy. If you, of course, if you are doing it manually, but if you are doing it using a code, it becomes very easy. But if you are doing it manually, then the square root, for instance, if we are doing it mod 7, you've seen that the square root of 4, therefore, the square root of 4 will be something like will be 2, negative 2. But this one is easy. But we have values that whose square root is not easy to get. Like let's think of 5, for instance. Getting the square root of 5 mod 7 will not be very easy. Is that okay? Even the square root of 6 mod 7 will not be very easy if it exists. If it exists, it will not be very easy to get. Even the square root of 3, if it exists, it will not be very easy. But of 4, we can easily get. Is that okay? Of 3 is not very easy. But we can always get it. But what you're saying is there's a challenge in terms of getting the square root. And especially when you are dealing with very large fields. Like this is a smaller field. So maybe we can use trial and error to find the square root of numbers. The smaller field. But supposing you're dealing with a larger field, and in cryptography, we're talking about large fields for security reasons, then it becomes very hard to do that. So that is a challenge. But of course, we can always maneuver around it by use of codes. Is that okay? You write a code to do square roots for you. Yeah, there are various algorithms that you can find, you can use to do square roots. There are various algorithms, especially also in the real world applications, in the applications, there are various algorithms for doing it. But of course, they have limits. They have limits for doing that. We can, if you have a very big number, for instance, we may have algorithms that may take too long to compute the square root. They may take too long. And even some very big numbers, you may not even find the square root because the length of time required for those algorithms might be too long. So that is why we then talking of that challenge of getting square root. Those algorithms are there, but they cannot do for all, they cannot find all square roots. As the field becomes larger and larger, the speed of computation reduces. And at some point, it becomes very hard to compute for very large fields. For very large fields. And of course, and we know that if for this in cryptography, then what we require are those large fields. That's what we require. Now, the other challenge is security. And with the security, we are not saying that compression introduces insecurity. We're not saying that it introduces, it doesn't. Of course, it's supposed to enhance security. But how does insecurity come in? Insecurity comes in if compression is not performed well. If it's not performed well, then there is insecurity. For instance, supposing you are doing it in a way that can leak some sensitive information. And so if that happens, then we expect that there be some insecurity issues, security issues. But if it's just done well, then this cannot be a challenge. Now, so I did not include the code on the slides, but I have it. I have it on my original notes. So I'll just share the original notes here. The point at infinity. Yes. So you know what we are compressing is just what we are changing is the y value. So the point at infinity does not have the y value. It's just infinite. So it just remains like that. And also points like 6 is 0. Why the y value is 0? Again, since we do not have two y values, it remains like that. 6 is 0, 2 0. Why the y value is 0? So it remains, it's compressed already. So the only one we are compressing is where we have two different y values. And so we want to use a smaller space. That one we shall make it 0. The other one we make it 1. Yes. How will? Yes. How you look at it? You see, the point at infinity is not on the curve. It's not a point on the curve. Yes. This is just the identity. We just add it there, but it's not on the curve. So you see what you're storing are points on the curve. You want to store them and use a minimal size. So when you're storing, of course, this point at infinity is not there. But we always add it there just to ensure that, yes, so that we have, it forms a group, but it's not a point on the curve. Yes. And of course, if you're doing your code, and you want to sum 2 points so that they give you a point at infinity if they are on the same vertical line, it's you to define what your point of infinity is. You define what you want. For example, when I'm writing my code, I define it to be -1, -1. So that when I sum these two and they give me -1, -1, then it means they are on the same vertical line. And therefore, that is now the point at infinity. And what that point of infinity is. Yes, because it's not on the curve. Now, so this is my code for compression. Now, you look at this. This one is saying is on curve. So this part, this function will just be, I'm using it to determine, first of all, if the point is on the curve, so that I'm not compressing a point that is not on the curve. So if I'm given an elliptic curve, then the point that I'm supposed to compress must be a point that is on this elliptic curve. Is that okay? So that I should not be struggling to compress a point that is not on this curve. So this is then supposed to tell me, if I give it a point that is not on the curve, it's supposed to tell me this point is not on this curve. So I cannot compress it. Is that okay? Yes, so that I then only compress points that are on this curve. Then I have this function here. This is now what we'll be compressing. It's compressing this point. It's compressing the point on the curve. And you can see if the point is at infinity during compression, it returns none. It returns none. So this point cannot be compressed. It's already in compressed form. Is that okay? Yes, so it returns none if the point is at infinity. But if the point is not at infinite, like in this case, some point, and this point has x and y, then the x remains, and this y point is the one we'll be changing, odd. If it goes to odd, then odd is 1. Is that okay? 1 is odd. Is that okay? So if I write it odd, you can want to make it 1, but for me, I chose to have odd to represent 1. And then where it's not odd, then it means that this point is the x value, the y value is smaller. And if the y value is larger, then on my compressed point, it will just write odd. So that's how I chose it. But you can write it 1 if you want, as you modify. Then to decompress, you just do what we've said. You take the x value, and substitute in the equation mod p. So you can see the x value cubed, x times x times x 3 times. You can see where I'm underlining. Is that okay? Yes. That means x cubed. That is the right-hand side of the elliptic curve. The right-hand side of the elliptic curve is x cubed plus ax plus b. So just take your y and substitute in the right-hand side of the equation. So that will be x cubed, then plus ax, then plus b. And the answer that you get, reduce it mod p. Is that okay? Yes. So that gives you the right-hand side of the equation. And so that is what now we are calling y squared. And now you want to get the square root of what is on the right side. So the square root of what is on the right-hand side is our y. So I've written here, let y be the modular square root of the right-hand side mod p. So let this y be the modular square root of what is on the right-hand side mod p. And then after that, you will come up with the two y values. So you want to select which y. Is that okay? Because we are decompressing. I want to select which y, and I've said selected y. So if y is odd, And then we know that it will replace where if y is odd, and then you replace it with the larger y value. You replace it with the larger y value. But if y is not odd, you then replace it by p minus this y value. So what I mean here is this. Suppose I got y squared to be 4. Suppose my y squared was 4. The square root will be 2. Is that okay? Or negative 2. But the one I'm interested with is 2, the positive one. So I ignore the negative. So I take this positive. So that positive is the one I'm calling y. Is that okay? Positive 2 is what I'm calling y. So the other square root would then be p minus 2. That gives me 5. Is that okay? Because it was supposed to be negative 2. Supposed to be negative 2, which is still 5. But since I was not interested with the negative 2, I just took 2, which was positive. So I take these 2, subtract from p, and that gives me another y. So let me now read what I've written here. What I've written, I've said, let the selected y, and I'm saying, if y is odd, if the parity there was odd, then I'll pick the y that I get, y that I got from the square root, the positive y. Else, that means if the parity is not odd, then my y value will be p minus y. It will be p minus y. So that if my y was 2, then this other one will be 7 minus 2, which is 5. So that is what it means. So I was decompressing. Then I just come and take the x that was there, then the y that I've selected. X and the y that I've selected gives me the point. Now, but if this point is not there, then what I get is the point at infinity. But now, this is where I'm doing the modulus square root. So modulus square root is done here, not here. Here, what this one is happening is that I want y, and then this decompressed function calls on modular square root function. Calls on the modular square root function, and the modular square root function does the work of getting the square root. So the modular square root function is this. This is what gets the square root. So how does it get the square root? Of course, it will be doing that using the Lagrange symbol that we talked of. The Lagrange symbol, that time we call it AP. And we are saying that if the Lagrange symbol is 1, then it has a square root. But if it's not equal to 1, then it has no square root. So the Lagrange symbol is what it's then using. That's what I've said, that if the Lagrange symbol AP is not equal to 1, then there is no square root. Is that okay? But if it's 1, then we know that that number has a square root, and we can determine the square root for that number. So to determine the square root of that number, then we begin by letting Q be P and S be S, and then we proceed into the loop. We proceed into the loop. And so on. So inside this loop, what we'll be doing is this. What we'll be doing is this. We are looking at mode 7. So first of all, we have 0. We substituted 0 into the equation on the right side and gave us 4. So we come here and get the square root of 4. Then next, we substitute 1. That's why he's saying that you're adding plus 1. We are moving one step by one. So we then go to 1. We substitute 1 in the equation on the right side. The value we get, we come with it here to get the square root. Then next we'll move to 2. Substitute 2 in the equation on the right side. The value we get, we come with it here, and you again get the square root. So that is what is happening here. It's a sequence of step by step doing for each of the values step by step. It's a very long process. Then we have the main function. The main function is where you define the elliptic curve. You can see my elliptic curve A, I've defined by 3. B, I've defined by 4. And P, I've defined by 7. I'm using U8. These are very small. I'm dealing with very small values. You can change to U32, you can change to U64, and so on, so that you can deal with the even larger elliptic curves. And then this is the point I want to compress. 2.5. This is the point I want to compress. Of course, I expect it to give me 2.1. But in this case, I've defined it to give me 2 odd. 2 odd. Because you can see, if this is 2.5 and I'm doing it mod 7, the other point is supposed to be 2.2. Is that okay? The other point, the inverse of this is supposed to be 2.2. So this 2.5 is then supposed to be 2.1. If you go by the examples we've been looking at. But for the case of this code, then I expect it to give me 2 odd. 2 odd, where odd stands for 1. Okay, let's run this code. Yes, it has compressed the points and has told me that it's giving me some points. So it's telling me that this point exists. Oh, okay, it's true. It's true. I used true, not odd. True. So true is the one it gives me. Okay, let me use a smaller value and see what it gives. Let me use this is 2.5. So what about 2.2? What will it give me if it was 2.2? Now, so okay, before that, it's also telling me that this point is not on the infinity. It's not a point at infinity. It's also telling me that. Then decompressing, it decompress the point back and give me the original point, which is 2.5. Let me use 2.2 and see what it gives. Is it off? What happened? Imezima maneno. Imerudi. Imerudi. Okay, the way I designed it is it's supposed to give me true if the point is larger and false if the point is smaller. if the point is smaller. Like in the case when you are doing it, when you are doing a calculation, we were using 1 and 0. So you can modify this to give you 1 and 0. Is that okay? So that when the y value is larger, it gives you 1. And when the y value is smaller, it gives you 0. But for mine, it's giving me true and false. False for smaller value of y, and true for larger value of y. Now let's try another point. I don't know whether this point is on the curve. I don't know. I've not tried. Let's just try this point and see. If it's there, it's supposed to tell us. And if it's not there, again, it's supposed to tell us that this point is not on the curve. Maybe it can panic or something. So I'm trying 3, 2. It has panicked, so that means that 3, 2 is not on this curve. 3, 2 is on the curve, so it says the main thread panicked. So the assertion failed. So the curve is on the curve. The point is on the curve. This is where the problem is. That function, the function curve is on the curve. This function is the one that panicked. So is the function here. This part is where the panic is on the curve. So this is where it has panicked. It's checking this point and seeing that this point is not on this curve. It's not on this curve. So it cannot compress it because it's not there. But when you try a point that is there, then it will compress that point. Now, so the other thing that I may request you to do, for instance, just as a way to modify, you can now come up with a code that can give you all the points at once and their compressed equivalent at once. Is that okay? So it tells you, for instance, this curve has these 10 points and their compressed form is here. Is that okay? Yes. So that's what. But for mine, what mine is doing is that I'm giving it a point at a time, and then I want it to compress that point. So you can modify yours and see whether it can, first of all, determine all the points on the curve and then give you their compressed form on the curve. So there are various things you can do to modify this code. Now let me just again share the notes for this. I said that the notes for this code, I had not included it in my slides, but I have them somewhere. So those are the ones I want to share now, so that the video would then capture them. Okay, these are the notes for the code that I've just shared. I think they're clear. Now, so the first function is on curve, and I've given the purpose of this just to ensure that the point that you're trying to compress is on the curve. So what it will be doing, therefore, it will be taking this x value, substituting it on the right-hand side, and see whether the result will be the same as this y value squared. Is that okay? So for instance, supposing I have, supposing this is the point, the y, the elliptic curve, x cubed plus 3x plus 4. And supposing the point that we're checking is 2, 2. So what it does, it takes this x value and substitutes there on the right side. So that would be 8, the right-hand side. The right-hand side would be 8. That is 2 cubed will be 8 plus 6 plus 4. Of course, this is same as 4. This is same as 4. Is that okay? Then it takes the y value and substitutes it here on the left-hand side. So left-hand side. Puts y. So y is 2. So 2 squared again is 4. So if the left-hand side equals the right-hand side, then this point knows, this function knows that this point is on the curve. So then the point can now proceed to the other functions. Is that okay? To be considered, either for the square root, what and what, and so on. Like the one that panicked, it was, I tried 3, 2, this point. So it takes the x value and substitutes there. So x cubed, this will be, this is 2. We are doing it mod 7. This is 2 times that, this is 6. 2 times 3, that is 6. Because this 3 times 3 is 9. Mod 7, that is 2. So 2 times 3 then be 6. Then plus 3x. X is 3. This again is 9 mod 7, which is 2. 9 mod 7, which is 2. Then plus 4. So this is 8. 8 mod 7, that is 1. Then plus 4. The right-hand side, therefore, is 5. The right-hand side, therefore, is 5. Is that okay? Then it now checks the left-hand side. The left-hand side. 2 squared will be 4. 2 squared will be 4. These two are not equal. So then it panics. It cannot proceed because it's now dealing with a point that is not on the curve. So it cannot proceed. So you only give it a point that is on that curve. So it has verified that this point is of course not here. So that is how that part will be doing to confirm if points are on the curve or not. Then from there we have the compress function. Of course, that one is just compressing. It's compressing. So of course, it maintains the x value and changes the y value. Is that okay? So the y value is what it will be changing. It checks if the point is at infinity, and if the point is at infinity, it returns none. So this point cannot be compressed. And if the point is not at infinity, it returns the x coordinate and the parity of y. It returns the x coordinate and the parity of y. Yeah, so what I was referring to is, okay, so if the y value is odd, I had told it to return true, and otherwise it returns false. Otherwise it returns false. Then there is this decompressed part. The decompressed part, what it's just doing, it takes the x, substitutes back to on the right-hand side, then gets the square root, and then looks at the parity and replaces the correct value of 1. That's what it's doing. But we have this part from modular inverse, modular square root. It's getting the square root, and then the Lagrange symbol, The Lagrange symbol is, this is how we abbreviate it. That's the Lagrange symbol. This symbol is used to indicate whether a value, the value at the top, where the value at the top, A, is quadratic residue mod P. In other words, does it have a square root mod P? So that's what this symbol is used to determine. So it is used to determine if the value at the top has a square root mod the value at the bottom. So we call it the Lagrange symbol. And when we are doing that, we got an easier way of doing the Lagrange symbol. So Lagrange symbol works like this. This is how it works. So if it calculates, so it's A raised to P minus 1 over 2. So for instance, let me talk of 7 as our P. And I want to find if 2 has a square root. So this is what I'm doing. 2, 7. 2, 7. So how am I calculating this? This is how I'm calculating it. I take 2 raised to 7 minus 1 is 6 divided by 2. So that would be 3. A raised to, so 2 raised to 3 mod 7. That's what I get. So this is the same as this. That's how you calculate it. Yes, let me write it properly. Yes, from Fermat's little theorem. Yes, from Fermat's little theorem. So that's why it comes from. And then is used to calculate this, the Lagrange symbol. Yes. So it is, the Lagrange symbol is AP. And then how we calculate it, we take A, raise it to P minus 1 divided by 2, then mod P. So P minus 1 in this case, 7 minus 1, that is 6. Then divided by 2. So I wanted the square root of 2. So it's then 2 raised to 3 mod 7. Now, then this, it says, if the result here, of course, this is a result, you can do it by first powering algorithm or using any other method. If the result is 1, if what you get from here is 1, then it means that A, in this case 2, if you get that is 1, of course here it will not be 1, it will be 1. It will be 1 because 2 raised to 3 is 8. Is that okay? 2 raised to 3 is 8. And mod 7, this is 1. This is 1. Is that okay? So it then means, if you get 1, it means that 2 is a quadratic residue. What it means by quadratic residue is that 2 is a square, and therefore its square root can be obtained. Is that okay? Its square root can be obtained. Let's see 3. What about 3? We are taking 3 raised to 3 mod 7. So 3 raised to 3 is 3 times 3 times 3 mod 7. First one here is 2, and the 2 times that, this will be 6, which is the same as negative 1 mod 7. Is that okay? And it has said that if the result is negative 1, then 3 is non-residue. In other words, has no square root. Is that okay? In other words, 3 has no square root. So there are only 3 options. There are only 3 options when you're calculating the Lagrange symbol. The first option is that you can get a 1. The other option is that you can get a negative 1. And the last option is that you can get a 0. You can get a 0. And so if it's a 0, then it means that A is divisible by P. It's divisible by P. Is that okay? So if it's divisible by P, we can never talk of it having either square root. Because the square root will be 0. So that means that it will also be quadratic residue. It will also be quadratic residue. Because you've gotten 0. And the 0 has a square root. The square root of 0 is 0. So again, that is a quadratic residue. So that is how we calculate, how we determine the square roots using the Lagrange symbol. So I wish to stop at that so that you look at that. Of course, look at the code and see how you can modify that code to perform what we just agreed. And let your code give you all the points at once, and then their compressed forms at once. So you can stop at that, unless somebody has a question. Any question? You can stop recording therefore, Alex. Can you stop?